Alright, so today we're going to go over orbital notation. Alright, so the first thing we're going to talk about are the 4 types of orbitals. Now, you have to be able to do electron configuration to be able to do orbital notation. They kind of go hand in hand, which is why we covered electron configuration first. Alright, so first of all, let's talk. We talked about orbitals yesterday. What did we mention? What are orbitals? What did we say yesterday? What were they? In our electron configuration, what part of it was the orbital part?
Pencil?
Do you have another pencil?
Anyone remember?
I don't know if I have one. Hold on. The exponent.
I'll take the notes and then you can call.
Not the exponent. The exponent was the number of electrons located there.
Oh, is it a P?
Yes, the S, P, D, and F. Okay, those were our orbital shapes. All right, so I told you we would talk more about it tomorrow. So today is tomorrow. All right. So what is an orbital? So an orbital is a region of space you're most likely to find an electron. So it's like a 3D region of space where you're most likely to find an electron, because we can't exactly pinpoint where those electrons are because they're really small and they move really fast. So now we're saying this is a 3D region on our energy level where we're most likely to find an electron. All right, and there's 4 types of orbitals. So we're going to be using an XYZ plane. So I always do my Z going straight up and down, and then my X and Y. All right, and when we do this on paper, it's very 2-dimensional. So I brought out my meter sticks to show you how we're gonna make this 3-dimensional. So 2-dimensional is like this. All right, so imagine this. This is what's on the board right now. All right, so you have to imagine instead that these ones coming down right here, if I don't hit myself in the face, these coming down are the ones coming out at you. The ones back here are the ones going into the board. So this is our 3D plane. Normally you see an XY plane. An XYZ plane is a 3-dimensional plane. Okay, so that's how we're gonna make these 3D, is by using the XYZ plane, a 3D plane.
So we put a Y, like left side of the Z too, or is that the place that we should put
Like
the Y?
here,
Like here? No, like on the other, yeah, there.
you can put it there. It's the same thing, it's still that line. All right, so our first orbital is an S orbital. All right, and an S orbital has a spherical shape. A spherical shape. So an S orbital in 3 dimensions would be like a sphere, a ball. So to draw it on our 3D plane, it would just be a circle, a ball. Simple as that. There's only one type of S orbital. It's just a sphere. One type. We good?
I spelled spherical. Spherical.
I did too, kind
Now it's forever on my YouTube video. Alright, so our second type of orbital is going to be a p orbital. Alright, and a p orbital has a dumbbell shape. Dumbbell shape. Which is kind of like this, right? A dumbbell. So I draw it like an 8. Kind of like that. So it would be if I took 2 of the s orbitals and I connect them. I have 2 spheres connected. That would be like my dumbbell shape. Okay? So there's 3 types of p orbitals. Alright, so let's go ahead and label our axes. So we have Z, X, Y, Z, X, Y, and Z, X, Y. So it's really important that we label our axes because our 3 shapes are dependent on which axis that we put it on. Alright, so our first p orbital is a p Z orbital. Alright, so we're going to draw this shape, two spheres, on the z-axis. So that would be our PZ orbital.
Is the next one a PX?
Yeah, so let's do PX next. So that would be our dumbbell shape, but this time it's on our x-axis. And what do you think the last one's going to be? PY, and it's going to go along our PY axis, which my pen is off here. So let me try that again. There, a little better, along the y-axis. So three types of p orbitals. We have the px, py, and pz orbital, which would be two spheres connected. Good? All right. Next one is a d orbital. So there are 5 types of d orbitals, and a d orbital takes on a clover shape, like a 4-leaf clover. So it's basically like taking 4 s orbitals and connecting them all together. Now I'm going to draw them. Honestly, you don't have to draw them if you don't want to, if you just want to label them. The main thing that I need for you to remember is that there are 5 types of d orbitals. So if you just want to write real big on your paper 5 types, write that. If you want to draw them, you can. I'm going to draw them, but you're not going to be required to draw them. The ones that you need to know how to draw are the S and P, the ones that we just did, which I think are pretty doable, okay? Now these ones get a little crazy, okay? So that's why you're not required to draw these. If you want to, you can, but you just need to know what? What do you need to know? 5 types, okay? All right, so I'm gonna go real quickly and label my axes, so I don't have to do that later. So ZXY, ZXY, ZX. All right, so the first type, I'm gonna start up here, is a DXY. So instead of this shape going on the X and Y axis, it goes between the X and Y.
The twunks.
So if this is my X and Y, I would have one here, one here, one here, and one there. Between my X and Y axis. Next, I have my DXZ. So this time it's going between my X and Z. So here's my X and Z. So I would have one here. Well, it's really hard to do when my pen is so far off. But so one here, one here, one here, one there. Kind of like that. Then I have my DYZ. So this time it's going between my Y and Z axis. So one here, one here, one here, one here. So they're just basically rotating around the axis is what it's doing. Now the next one is the DX squared minus Y squared. So this time it actually goes on the X and Y axis. So you have one along the X and one along the Y. And then the last one is the DZ squared, which this one is crazy. So you have one going up on the Z axis, and then you have one like going around it, kind of like it's orbiting it like orbiting like a planet or something. Pretty crazy looking. So what do you need to remember? 5 types. 5 types of D orbitals.
What is the last one?
I know, it's crazy. That's the DZ squared. You have one on the Z, and then you got this one floating around it. Like a ring around a planet. Doesn't even look like a clover anymore.
It's like a planet.
So 5 types of d orbitals. 5 types. So we had how many types of s orbitals? 1. How many types of p orbitals? 3. How many types of d orbitals? 5. So going in that pattern, how many types of f orbitals would you say there are? 1, 3, 5, 7. And we're not even going to attempt to draw those. They're not even in your textbook. So we're not going to try and draw those. Just know there are 7 types of f orbitals. 7 types. But we haven't done much with the f block, have we?
No.
I told you you wouldn't have to do that in electron configuration, so you won't have to in orbital notation either. Alright, so moving right along. Alright, so when we do orbital notation, there's 3 rules that we're going to have to follow. The first one is the off-ball principle. Okay? So the off-ball principle, and I mentioned this yesterday, but the off-ball principle says that we're going to fill electrons, so fill electrons into the lowest energy levels first. Now, we've been doing this the whole time. So back on Monday, when we were putting electrons on the energy levels, did we start with energy level 5, or did we start with the first 2 on the first energy level?
First.
We started with the first energy level, and we did 2 there. Then we moved to the second energy level, and how many could go there? 8, right? So we always filled with the first energy level, then we went to the second, then we would move to the third, then we would move to the fourth. We don't ever just start with the 4th energy level. So we've been following this rule the whole time, that we fill the lowest energy level first. So we're going to continue that when we do our orbital notation. We're always going to start with the 1s, and then the 2s, and then the 2p, and then the 3s. Now this also explains why we do the 4s before 3d. And that's because our 4s orbital is lower in energy than our 3d. So that's why we're going to have to do 4s before 3d. Which that's why our d block is shifted down a number. It's higher in energy. Okay? So that's the off-ball principle. Off-ball. Good?
No. Oh, yeah,
Are we good? Alright. Next one is the Pauli exclusion principle. Pauli exclusion principle.
Please excuse the interruption. Any senior who is going to be off campus in the afternoon, please come to the small gym for tux and drape pictures at this time. Again, any senior who is off campus in the afternoon, please come to the small gym for tux and drape pictures at this time.
Alright, Pauli exclusion principle states that electrons, or let's put it as only 2 electrons can enter one orbital, and they must be spinning opposite directions. So electrons are spinning. Alright, and for them to share the same orbital space, they're going to have to be spinning opposite directions. Alright, so how we're going to represent an orbital is with a dash. So this is going to be an orbital. Alright, and we can only put 2 electrons in each of these orbitals. So each of these dashes can only have 2 electrons. So we're going to show electrons as arrows. So to show that they're spinning opposite directions, we're going to have one arrow go up and one arrow go down. Now, if we're filling in 25, 30 arrows, that can take a lot of time. So a lot of time you can see them written as half arrows. So they'll look like this. It's the exact same thing as this drawing. It's just these are half arrows and they're still showing opposite directions. It's just that these takes less time to draw. That's the only difference. Half arrows, full arrows, whichever you prefer is perfectly fine. They just have to be going opposite directions.
I'll have them going
It's just right here.
Thank you.
I told her that she has a different report down there. So it's under Kelsey Jones. Put my name on it, and I'm putting number.
Alright, so that's how we're gonna do this. The Pauli exclusion principle. We can only put 2 electrons in one orbital, and we have to show them with opposite directions, opposite facing arrows. If you want to do full arrows, cool. I'm doing half arrows. You can do half arrows with me. Okay? Alright, and the last rule that we have to follow, it's not going to make much sense until I do the first example with you, but let's go ahead and write it. And the last one is Hund's rule. And Hund's rule says that for each sub-level, whoa. There's not an E there. Let me erase that. I was getting ahead of myself. For each sub-level, an electron must enter each orbital of the same spin before doubling with opposite spin. So it probably doesn't make very much sense. So let me give you an example. If I had a 2p sublevel, how many different p orbital shapes did we draw? 3, right? So I would put 3 dashes. There's 3 p orbitals. Let's say I had 4 electrons. Okay? I couldn't do this. Because what this says is that for each sublevel, which my sublevel would be 2p, I would have to have 1 electron enter each orbital going the same direction before I could go back and fill one of them. So instead, I would have my 3 orbitals and I would have to do 1 going each direction, and then I could come back and double the 4th one there. So I have to have 1 going each before I go back and double.
That's good. That's that scared me. Oh my lord.
Okay? Alright, so our first example is going to be oxygen. Alright, so find oxygen on your periodic table, because the first thing we're going to have to do is write the electron configuration. That's the very first thing we have to do. So find oxygen on your periodic table. Alright, so someone who wants to volunteer and give me the electron configuration starting at 1s for oxygen. Alright, Chloe, what do we got?
1s squared, 2s squared, and
2p to the 4th. Good. Alright, so the first step for orbital notation is that you write the electron configuration. So they really go hand in hand. Alright? So now, first rule, off-ball principle. We're going to start with the lowest energy level first. So I'm going to come down and I'm going to write my 1s on the bottom, then my 2s, and then my 2p. Because the lowest is on the bottom, my highest is on top. Now, how many different shapes do we have for the s orbital? 1. Just 1. So it doesn't matter that this is my first energy level. There's only 1 type of s orbital. This is my second energy level, but there's only 1 type of s orbital. This is still my second energy level, but how many types of p orbitals are there? 3. So 1, 2, 3. So now we go in and fill our electrons. So Pauli exclusion principle, we can only put 2 electrons in each orbital. And remember, our electron numbers are the exponents. So how many electrons are in our 1s? 2. So opposite arrows. How many is in the 2s? 2. So opposite arrows. And now, how many is in my 2p? 4. So Hund's rule. I have to put 1 in each going the same direction before I go back and double it with the opposite direction. Just questions on that one? So that would be the orbital notation of oxygen.
It can't be easy. It can't be easy.
That's it. Alright, let's do, other questions? Before we do another one? Alright, let's do another one. Let's do nickel. So find nickel on your periodic table. Thank you. Have a good day. Bye. He called me sweetheart today.
I found it.
Alright, Kyle, give me the electron configuration of nickel, starting at 1s.
1s2, 2s2, 2s6.
P.
Oh yeah, 2p6,
Uh-huh.
3s2, 3p6, and then it was 2 or 4s2,
Uh-huh.
and then it's d3, 8.
3D to the 8. Perfect, because once you hit that D block, you gotta drop down to 3. Alright, so now we come down and we follow this order. We just drop with 1s on the bottom. So 1s, 2s, 2p, 3s, 3p, 4s, and then 3d. So I just copied that, but I started with 1s on the bottom and then worked my way up. Alright, so now all of the s's are going to get how many orbitals? 1. So I can go in and put 1 dash for any s. All of the p's are going to get how many orbitals? 3, because there's 3 p's. And how many will my d get? 5, because there's 5 different types of orbitals for the d. 1, 2, 3, 4, 5. Perfect. If we had an f orbital, how many different orbitals would we draw? 7, but you won't. Alright, so now we go in and we fill in our exponent numbers. But question for you, would I ever skip and not fill in one of these?
No.
No, they would always be filled, right? That's the off-ball principle. We always fill those first. So you can go in and just fill in all the way up to the top. But check the last one. So let's fill in all the way to 4s and stop. Don't do the top one yet. So fill in all the way to there. That's why I like my half arrows, because I feel like I can do those a lot quicker than full arrows. Because we would never skip and not fill this one and go here. We would never skip that. The only one that would possibly not be filled is the top. So now, how many electrons are in the 3D?
8.
8. So I have to put 1 in each, right, before I can double any of them. So I'm going to do 1, 2, 3, 4, 5. Now I can go back and do 6, 7, 8. And that would be my orbital notation for nickel. So on your quiz on Friday, you have to do the electron configuration, the noble gas configuration, the shorter way, and the orbital notation. All 3. Questions? And they do this in freshman chemistry in college. Now, there is a way to where this won't take up as much paper. Alright, so you can do this side to side. I like doing it up and down because you can look and say, all my S's get 1, all my P's get 3, okay? But you can do this side to side. So let's do an example of that way just so you can see how it's done. So let's do chlorine side to side. Alright, so chlorine. Find chlorine. Alright, and Nevaeh. Give me the electron configuration for chlorine.
1, 2 to the second.
1s squared.
Oh, yeah.
Yep, uh-huh.
2s squared. 2p to the 6. 3s squared. And 3p to the 5th.
Good, 3p to the 5th. So to do this side to side where it won't take up such a big amount of room on your paper, is we would start going with the 1s. Alright, but as you go, you put your blanks in. So I know a 1s gets 1 blank. Now I do 2s. How many blanks would that get? 1, because it's an s. Now I do 2p. It's a p, so how many orbitals? 3. 1, 2, 3. Now I do 3s. So how many orbitals? 1. And now I do 3p. How many orbitals? 3. So basically you do it as you go. I like doing it up and down because then I can just put all the s's get 1, all the p's get 3. I like doing it that way, but it does take up a lot more room on your paper. So you do have the option to do it this way if you prefer. It doesn't matter. It's just you need to go left to right or bottom to top. Do not do top to bottom. Because if you do it the up and down way, you need to show that the lowest energy level is on the bottom, not on the top, okay? So now we would fill in our electrons all the way to the very last sublevel. And then how many is in my last sublevel? 5. So I would do 1 in each, and then I could go back and double 2 of them to get 5. Okay? Questions about orbital notation? Alright, so here's what I want you to do. You had 6 elements that you did yesterday. Some of you already got your papers back. There's 2 people's papers that are up here that I'll give you back here in a second. What I want you to do is do the orbital notation for those 6. So do those 6. Okay? So you either have your paper back or you still have it. Do the orbital notation for those 6. So I'll write the elements up here just in case you don't have them. So it was magnesium. Fluorine. Number 3 was cobalt. 4 was phosphorus. 5 rubidium. And 6 tellurium. So I want you to do the orbital notation for those and then turn it back in. If you want to do it on the same paper and turn it back in if you've already turned it in, or finish that up and turn them both in together so you can get both grades. Okay? And Jillian, I'll give you your paper back right now.
Okay.